So hello everyone. Our today's topic is Orgel diagram, and Orgel diagram is for the high spin complexes. So before going into detail of these complexes, in free metal 5d orbitals they are degenerate. In free metal ion all the d orbitals are of same energy. But let us see their shapes and their arrangement in the complexes. So when we see the shapes of d orbitals, say dxy, dyz and dzx. In these cases, lobes are in between the axes. But in dz square and dx square minus y square, lobes are on the axis. So their shapes is different. For dxy, dyz, dzx, they are of one type, and dz square and dx square minus y square they are of different type. Now see the arrangement of ligands. So in octahedral arrangement, ligands are on the axis. So the lobes of the d orbitals which are head on to the ligands, they feel more repulsion as per the arrangements, because ligands have electrons, orbitals have electrons. So when they are head on to each other, they repel more. And if they are in between the axis, they repel less. So in this way, d orbitals split into two parts according to crystal field theory, and this T2G, which is of lower energy, and Eg of higher energy, and this is the very center. So T2G is of lower energy and Eg of higher energy, because Eg set of orbitals, their lobes are on the axis and ligands are also on the axis in octahedral arrangement. This is the splitting in octahedral arrangement. And T2G set, that is dxy, dyz, dzx, lobes are in between the axis, but ligands are on the axis. So they are not head on to each other. That's why their energy decreases. And this total energy is delta O. Now decrease is divided among three orbitals. That's why it is minus 2 by 5 delta O, and increase is divided between two orbitals. So it is plus 3 by 5 delta O, and delta O is 10 dq. So in this way it is equal to minus 0.4 delta O, or we can say 4 dq, minus 4 dq, sorry, and plus 3 by 5 delta O, that is equal to plus 0.6 delta O, or equal to plus 6 dq. So Eg set is of higher energy, T2G set is of lower energy in octahedral arrangement. Now see it in other way around. When we talk about tetrahedral arrangement, ligands are in between the axis. See, this is x-axis, z-axis, y-axis. Ligands are in between the axis. So now which d orbitals repel more? Obviously this set dxy, dyz, dzx, whose lobes are in between the axis. So in tetrahedral arrangement, this goes other way around. In free metal, these are 5d orbitals which are degenerate. Now they split into two parts, but other way around. In octahedral, it was T2G at lower energy, Eg at higher energy. But in tetrahedral, two orbitals, that is doubly degenerate. This E and T2 means, E means doubly degenerate, T means triply degenerate. In octahedral we write Eg and T2G, but in tetrahedral we write it as E and T2. G is omitted. Now E and T2, and this splitting is delta T. Delta T is always less than delta O, and that is equal to 4 by 9 delta O, because splitting due to 4 ligands in tetrahedral, that is less than splitting due to 6 ligands in octahedral. Okay, so increase is divided among 3, so it is plus 2 by 5 delta t, and decrease between 2, so it is minus 3 by 5 delta t, so that is minus 0.6 delta t plus 0.4 delta t. So you can see when octahedral arrangement is there, then it is T2G EG, but when it becomes tetrahedral, then splitting is reversed. Okay, now come to the electronic configuration. So first D1. So D1 is, this is T2G EG. I am talking about octahedral only. And then in tetrahedral we just reverse them. That's it. Okay, in D1 there is one electron. In D4 it is like this. D4 all high spin, because Orgel diagram is meant for high spin complexes only. Okay, now D6, 1, 2, 3, 4, 5 and 6. Now D9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the arrangements. Now look at these arrangements. So in D1 there is promotion of one electron from T2G to EG, and there is one transition only. One transition is observed. Now come to the D6. So in D6, say from T2G to EG, only one electron is there whose spin will remain same in T2G and EG. That is, delta S is 0 for only one electron. For other electrons, if we see 1, 2 and 3, if we transfer them, if we shift them to EG, their spin will change. If the spin will change, that is a forbidden transition. You know, for a allowed transition, delta S should be 0. So there is only one electron, for that delta S is 0. Means there is only one spin allowed transition, and only spin allowed transitions are allowed in Orgel diagram. And otherwise, you know, spin forbidden transitions, their intensity is very low. So only permitted transition is 1. So only one electron transfer is the feasible. So D1 is similar to D6. So D1 and D6, their arrangement is same, splitting is same. Now come to the D4. If you talk about D4, if you transfer one electron from T2G to EG, it seems like one hole. This is the hole. Okay, vacant orbital. One hole is transferred from EG to T2G. See, electrons are 4, hole is 1. So we are talking in terms of hole. There is one hole in EG, and when electron is transferred to EG, there is one hole created in T2G. So it seems like the transfer of hole from EG to T2G. That's why its diagram is inverse of D1. Diagram of D4 is inverse of D1. Same is the case with D9. In case of D9, if one electron is transferred, say there is one vacancy in EG. So when one electron is transferred from T2G to EG, it looks like one hole is transferred from EG to T2G. So D4 and D9 are similar. And arrangement of D1, D6 is opposite to D4 and D9. Now let us find out their ground states. D1, D4, D6, D9. So what is the value of L? You know, L is summation of ML. So it is plus 2, L is 2. So L2 means D state, because you know L 0, 1, 2, 3, 4, 5. S, P, D, F, G, H. It's like that. Okay. So D state for D1. What about D4? What is the value of L? 2 plus 1 plus 0 minus 1. Again 2. Again it is D state. D6. Plus 2 plus 2 plus 1 minus 1 minus 2. That means again 2. Again D state. D9. Plus 2 plus 2 plus 1 plus 1 plus 0 plus 0 minus 1 minus 1 minus 2. Again L is 2. Means all of them have D state. And you know, D configuration, D orbital, D subshell is same as the D state. And you know, D state split into D state for free ion, split into T2G and EG Mulliken symbols. In complexes. Okay. In octahedral, it is split into capital T2G and capital EG. And in case of tetrahedral, it is T2 and E. G is omitted in tetrahedral. That's it. Okay. So now, if you draw the diagram for D state and there is ligand field, in free metal ion it is D state, but in case of ligand field they split into two parts depending upon their electronic configuration, like D1, D4, D6, D9. So if we talk in terms of D1, one electron transition, promotion of one electron from T2G to EG. So it is T2G and it is EG. Okay. And if you see the S value for it is half. So 2s plus 1 becomes 2 into 1 by 2 plus 1 means 2. So that means it is 2s plus 1 L and J. No need of J here. So 2s plus 1 L means it is 2D. 2D for D1. And if you see the D9, it is similar to this. It is also 2D. Because only capital S comes out to be plus half. Here what is S? Half, 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 half means 4 half, 2. So 2s plus 1 comes out to be 5. Here again 4 unpaired electrons. So 2s plus 1 comes out to be 5. So it is 5D. It is also 5D. So 2 are 2D, D1 and D9, and D4 and D6 are 5D. So for D1 it is 2D. So 2D it is 2 T2G and 2EG. And if we have D9, it is again 2D, but now it is other way around. Why is it so? Because there is seems like promotion of the hole from EG to T2G. That's why now it is like 2EG to T2G. So this is D1, this is D9. Now D4. D4, it is 5D. So they again split, but say D4. D4, there is a transfer of hole from EG to T2G. So it is just like D9. And in D6, there is promotion of one electron, and therefore it is just like D1. So when we draw their configuration, D4, it is 5 EG to 5 T2G, and in case of D6, this 5D is promotion of one electron from T2G to EG. So it looks like this. So if we combined all of them into one diagram, that is called Orgel diagram. So we keep the free state, that is D state, at the center and draw like this. It is T2G 2 or 5. It is EG 2 or 5. This is D state. Okay, at the center. Now T2G to EG, promotion of one electron from T2G to EG, that is for D1 and D6 octahedral, right? And if we see the promotion transfer of hole from EG to T2G, that is for D4 and D9 octahedral. And as I said earlier, for tetrahedral, it is other way around, because in octahedral, ligands are on the axis, but in tetrahedral, ligands are in between the axis. That's why for D1, D6 octahedral, same is for D4 and D9 tetrahedral, except G's word is omitted. Okay, and here it is D1 and D6 tetrahedral. So this is all about Orgel. This is combined Orgel diagram for the D state. And keep in mind, for Orgel diagram is applicable for high spin complexes and spin allowed transitions only. Here we show only spin allowed transitions, and at the same time this is average energy. This is for free metal ion. This is very center actually. And as ligand strength increases, difference between T2G and EG increases, and again here ligand strength. So on the both sides, if ligand strength increases, difference between T2G and EG increases. At the same time, it is a qualitative. We cannot calculate energy here, but we can qualitatively see that energy difference is increasing as the ligand field increases. And strength of the ligand we can see from the spectrochemical series. Thank you very much for watching this video. Do like the video and subscribe my channel. God bless you all. Happy learning. Jai Hind. Jai Bharat.